good morning, everyone. How did your homework go? Any questions? So we look at so number 13 and 28. So ratio test. Right. So we have the following series, sigma k squared over 4 to the k, and the question, does it converge or diverge? So this is a series where the only test basically we can use is the ratio test, because the limit comparison, we don't know what to compare it with. We only can compare it basically to itself because we don't really have many choices in here. So we're going to use the ratio test. Okay. Now to do the ratio test, we have to identify AK. Sorry. 4 to the k. And we have to identify AK plus 1, which is we substitute k plus 1 for k in every term, okay? And then we have to evaluate the ratio and see what we get. So we take the ratio of AK plus 1, basically absolute value of that over the absolute value. But in this particular problem, the terms are positive, so the absolute, they are equal to their absolute value. So this will give me the following. Divided by k squared over 4 to the k. So this would give me the limit as k goes to infinity of. Now we do the property of fractions times 4 to the k over k squared. So, and then we, as I said yesterday, we kind of try to put the like term together. So this would give me the k plus 1 squared over k squared. Remember, we have to compute the limit of this expression. We have to find the limit. So to find the limit, first we try to see if we can do some simplification, and then we proceed. So that's the limit of. We need the limit of this term here. So one easy way to do it, you can either expand that, but I think it would be easier to put them all to the power 2. That would be easier to handle. And we multiply this by 4 to the k over 4 to the k plus 1. As we said yesterday, this is 4 to the k over 4 to the k plus 1. So we can rewrite this like that. And this would give me 1 over 4. Now we find the limit as k goes to infinity. All right, k plus 1 over k, the one inside here, when k is large, this will go to 1. So the limit, k plus 1 over k, we divide by k both sides, this is equal to 1, and that will leave me in 1 4 less than 1. So if the ratio is less than 1, by the ratio test, series converges. Okay. Question as we proceed. So now let me look at number 19, and then we have a look at number 28. And okay, so it's sum of 2 to the k over k to the power 99. and my k goes to 1 to infinity. So again, this have the same issue. Limit comparison actually doesn't get me anywhere. So I'm going to use the ratio again. So, and then I'm going to ask you a question, see if you guys can answer. A to the k equal 2 to the k over k to the 99. The terms come after over, instead of k plus 1 to the 99. Now I use the ratio test. So let me evaluate the ratio in this scenario. Over AK and see what we get. We get the limit as k goes to infinity of 2 over divided by 2 to the k over k to the power 99. Okay, so finally this will give me of 2 to the k plus 1 over times k to the 99 over 2 to the k. Now I will do exactly what I did in the previous problem. We're going to put like term together. So I will have k to the 99 over k plus 1 to the 99 times 2 to the k plus 1 over 2 to the k. Right. Now we have to compute the limit. We have to simplify. Right. What do you want me to do now? So far I'm just doing algebra. Now I need to compute the limit. How would we do it?
Well, and for the second one, for 2k plus 1, can you simplify that to become 2k times 2?
Right, and then so 2k plus 1 over 2 to the k can be split. And this would give me honest to goodness 2. All right, so this will give me a 2. So I took care of that term. What do you want me to do with that term? Because we want to find the limit and we have to find it correctly.
Do we do the same thing we did in the problem before? Just put it link to the 99?
Exactly. So the easiest way is, like we did before, to put the whole thing to the power 99. The power 99 kind of scared us a little bit, rightfully so, but it's the same idea. And now we find the limit. This piece right here, when k becomes very large, this is going to become close to 1. 1 to the power 99 is 1. The whole thing is equal to 2. This is absolutely greater than 1. It means that the series, by the ratio test, the series diverges. Absolutely diverge.
I have a question.
Yes, of course.
Have we done one yet where, like, what does it mean when you have to change it from negative to positive when it's absolute value? Like, you know what I mean? Yeah.
Here? Yeah, we can use it. Let me give you a scenario. It's a good question. Let us say I have this series. I'm going to add something. This is my series. You see what I did?
Oh, so it's like
You see what I did?
yeah, so changes from negative to positive.
Right. In this scenario, actually the alternating series test is hard to use. Because alternating series tests, you have to show that those equal to 0. Actually, they don't, but I will mention that in a minute. And then you have to show that those are decreasing. So it's really even hard to apply the alternating series because of the type of terms we have. So in this case, this is going to become -1 to the k, and this would become -1 to the k plus 1. So it's an alternating series test is not really easy to justify. In this case, when I take the absolute value, the minus is going to disappear. You see what I mean?
Yes.
Yeah. So that's really what happened. If in case we have so the ratio test applies every time, even if I have negative terms, it really does apply. That's a typical scenario where I can have negative terms or alternating. Alternating series test is not very easy to use. It's kind of complicated to use, and then I can use the ratio test. And if I get a number bigger than 1, it means, you know, diverge, less than 1, converge. Equal to 1 is where I have an issue. Okay. Now, before I go on, a question. So the series diverge, I'm done with this problem. Intuitively, though, this is not, when k goes to infinity, what do you think is going to be the limit of that expression? Which one goes to infinity faster? Anybody have any idea?
Oh, k to the power 99, a lot faster.
You guys agree with him? What do you think? I know it's tricky. Okay, it's actually 2 to the k. 2 to the k goes to infinity faster than k to the power 99. Even though it's a large power, don't be cheated by that. Exponential goes to infinity faster than k to the 99. Actually, this limit is going to be equal to infinity. All right, let's see. If I apply L'Hopital's rule, okay, let me apply L'Hopital's rule to convince you of that. So what's going to be L'Hopital's rule? Now, the derivative of 2 to the k, or 2 to the x in general, is ln of 2 times 2 to the x. Okay, all right, that's the derivative of that. So if I apply the L'Hopital's rule, I will have the limit of ln of 2 times 2 to the k over k to the 99 is 99, k to the 98. Am I correct? When k goes to infinity, infinity over infinity, still I have to apply L'Hopital's rule again. I'm not going to apply it forever because it's going to be boring. I apply it again. ln of 2 is a constant. Derivative of 2 to the k, you have another ln of 2, 2 to the k over 99 times 98, k to the power 97. What do you think is going to happen if I keep applying L'Hopital's rule?
For the top one, are you just gonna keep adding like squares to the natural log of 2?
And what's going to happen here?
You're just gonna keep adding 97 to 96.
So eventually, if I use L'Hopital's rule like 100 times, and I mean it, what we're going to get here? 99, 98, then 97, then so on. So actually, I'm going to have something along the line of 99 factorial at the end, eventually, something along those lines. ln of 2 to a large power, probably this is going to be 99, 2 to the k. When k goes to infinity, this will go to infinity. So 2 to the k, which is goes to infinity faster than k to the power 99. Even though if you have a larger power, the exponential goes to infinity faster than k to any power you can imagine. Even if I put k to the power 100,000, 2 to the k goes to infinity faster. And this limit is going to go equal to infinity. But the numbers we have to put to see that has to be very, very large. So I cannot put really small numbers. So I have to take k like to be 1,000 to start realizing that 2 to the 1,000 is way larger than 1,000 to the power 99. Okay, so it's an interesting idea is that, of course, that's why you guys were not able to use alternating series tests at the beginning, because you don't see that this goes to infinity. But some result that you should know, the exponential goes to infinity faster than the power function, regardless what the power is about. So we finalize by looking at number 28, and then we proceed further. And what is this? It's along the same line. So you guys didn't ask any question involving factorial. Okay, k over e to the k. So let me ask you a question now. If I look at the general term, what's the limit of that as k goes to infinity? Just out of curiosity.
Want to be e to the k that goes to infinity faster.
Which one goes to faster?
E to the k.
So what's going to be the limit?
0.
Yeah. This limit here is 0. Or you can apply L'Hopital's rule. You get 1 over e to the k, which is equal to 0. Okay, so I mean, this means nothing. If the limit goes to 0, this means nothing. It's just so you can interact more and more ways, though, which goes to infinity faster. So e to the k, 2 to the k, 3 to the k, they go to infinity way faster than the power function. And the power function, like k, goes to infinity faster than the ln of k. That's really how it works. So now I'm going to use the ratio test. And then the rest is actually going to be verbatim the same as I did like the other problem. So I'm going to take the absolute value here and the absolute value. I'm taking the absolute value even it's positive because I want you to get into the habit of taking absolute value because we're going to need it in the next chapter. So that's why I want the habit of the absolute value. So if I do it and I flip the denominator, you're going to have that times the e to the k over k. And now verbatim, like we did before, going to give me the limit of k plus 1 over k times e to the k over e to the k plus 1. And then the same thing as I did, verbatim actually, times. Now e to the k, don't let e scares you at all. E to the k over e to the k plus 1, it's again e to the k over that, which is the 1 over e. So now don't let e scares you or anything. Now as k goes to infinity, this term here will have to go to 1, which leave me with the 1 over e. Definitely it's less than 1. It means my original series converges. Means the series converges. End of the problem. Okay. By the ratio test, of course. Any other questions from the homework?
So usually with factorial, or is that what they're called?
Yes.
Usually when it comes to those, it's practically the same thing, just we're dealing with the factorials and we have to.
Yeah, the principle is the same, but you have to be very careful working with factorial. Very careful. Okay, don't use any rule. Just use what's really allowable, like what we did yesterday. If you have n plus 1 factorial, you don't split the factorial. It's n factorial times n plus 1. So you have to be very careful how to use them, but the principle is the same. Okay, it's the algebra that you have to be careful with. Okay, so make sure you guys do the factorial for tomorrow because we need factorials a lot. So as far as tests are concerned, there is one more test called the root test, but I will not mention it. I don't think it's crucial. The tests we've done so far are the important tests that we are going to use. So in this section, we're going to talk a little bit about strategies, which test to use when, and then I'm going to give you a bunch of series and tell you, okay, which test do you think is the appropriate test? So a little bit about strategy. Now, the statement of each test, you have it. You guys should have a paper and write all the statement to make it easy for you to go back to them. I will talk about a strategy for choosing a test. All right. So first, what test do we see? First, we have the divergence. First, we saw the divergence test. In this case, whenever you have a series, so my starting point is that we have a series, sigma AK. Okay, just stare a little bit, glance at the term AK. Just look at it. If you realize the limit is not 0, very easily, you're done. If the limit is 0, nowhere. So divergence test, I usually say, look or glance at AK. Look at AK. Whenever you have a series, look at those terms. Are they blowing up or they are becoming small? That's the first question. If the limit not 0, immediately series diverge. And you will not have a lot of those cases because that's not what we're interested in. Limit equal to 0, inconclusive. Okay, and that's really our problem is what happened when the term becomes small, not really very small. And then second, we saw the integral test. Okay, works only for series with positive term, works for series with positive term. Okay, now when do we use it? First, that should be positive. When do we use it? Anybody has any feeling when to use it? Anybody likes to pitch in?
When the function is positive, continuous, and decreasing, right? That would be the
When to use it?
test.
When to use it? When to use it?
Okay.
When to use it? You're right. That's. But if you have a series, how can you decide that integral test?
If it's easily differentiable.
The other opposite of differentiation.
Or integratable.
Right. When the integral and this integral is easy to find. You have to be that. Okay, so you have to know each one. So in this case, let me remind you that f of k is AK, but that's really the idea. When it's easy to find. If it's not easy to find, drop it, impossible, move on. Then we have the limit comparison. Okay. The limit comparison also work for series with positive terms only. And the limit comparison, the idea is we have to look at the series and compare it with another one that we know its behavior. So we always compare them with either a p-series or a geometric series because those are the only one we know their behavior. But when it is a good idea to limit the limit comparison test. So here the idea is to compare sigma AK with another series, sigma BK, where we know the behavior of sigma BK. Where we know behavior of the sigma BK. So we compare it to something we know. Now I want to use it. That's ready. Use it when in general, usually I give you guidelines in general. I mean, it doesn't mean all the time, but in general, use it when the terms of the series The term of the series involve only constant power of n. What do I mean by that? Constant power of k, sorry. Okay, use it when the terms of the series involve only constant power of k. It means, let me explain what do I mean constant power. It means involve k squared constant power, square root of k4 plus 5. So if the term involves constant power, k squared, square root of k squared plus 5, etc., limit comparison. Because what's going to happen when the term only involve those type of terms, the ratio test will usually give you a 1. So that's really when we use the limit comparison, k squared, k cubed, as long as it's a constant power. Then we have the other test. So that's the limit comparison, and that's an important thing to keep in mind. And then we have the comparison, ordinary comparison test. Ordinary comparison test. This is hard to use because you have to build an inequality in this time. So here it has to be an inequality. We're not taking limit anymore. So we have to build an inequality. And then we know what it tells me. If the smallest, so if the largest converge, then the smallest will converge. If the smallest diverge, then the largest will diverge. Okay. When to use it? This is hard to use in general, unless it's an easy series where the inequalities can be built. Nothing hard about it. Usually it's hard to use. Use it, you may need to use it, but we use it as a last resort. Okay, that's harder to use because an inequality has to be built. You have really to build inequality. So use it. I'm not scaring you from it, but it's not always our first approach for that. And then the ratio test. The ratio test is very powerful, but sometimes it gives me a 1. Sorry. Okay. Oh no. All right. The ratio test works for all series. They don't have to be positive. Works for all series. Don't have to be positive series. Okay. But it has a pitfall. When the ratio is 1, we have actually a problem. So use it. And as I said, those are guidelines. When the terms of the series involve factorial, so involve factorial or exponential term. What do I mean by that? It means they involve k factorial. Sometimes we're going to have 2k factorial, and then exponential term, 2 to the k, 3 to the k, etc., etc., or a combination of them. So when the series or exponential or a combination of them. Now, whenever you have a series and you see 2 to the k, 3 to the k, k factorial, whenever those shows up, or a combination of them, immediately the ratio test. Okay. So finally, the other test we saw, alternating. This is a very restricted test. Use it when you have an alternating series in general, when the series alternate. And you have to make sure both conditions are satisfied of the alternating series test, or you cannot use it. And one nice thing about the property, so for the alternating series, also recall we have the following fact, that if the series converge, we can basically estimate if I use the first n term to estimate the sum, the error is always less than the first neglected term. So this is a very nice thing because it helps me to estimate the sum. So these are the main tests that we actually use, and this is when we use each one of them. And then other concept we study was the idea of the absolute conversion. So I will mention that. Okay. So absolute conversions. Okay. And this tells me the following. If a series is absolutely convergent, then the series converges. Okay. It means if when I plug in the absolute value of the k, if sigma k converges, then without them, also it will converge. However, vice versa is not correct. If a series converge, it doesn't mean it converges in absolute value. And this is where we introduce the idea of conditional conversion. Right. Now, this is a theorem, of course. It's a theorem, it's a fact. It's not like just any simple, that's really a theorem. Now, sometimes we can use this idea in showing the following type of series converge. So suppose let me use an application to that. Study the convergence of the following series. Let us say I put sigma sine k over k square to infinity. Okay. All right. So here the ak, it looks is the sine of k over k square. Okay, so I introduced the sine this time. First time, probably I give you an example like that. All right. Okay, let's look at this series. How can I study its conversions? Any ideas? Question number one, is it a series with positive term?
Yes.
Are you sure? Why? Everybody else?
Yeah, I think it's positive.
Why?
Well, k can't be a negative number, but I don't really think that would even do anything.
I agree. What about the sign of it? How was the sine graph?
Oh, its sine graph is oscillating. I don't know if that's the right word, but it's going positive and negative.
Right. Why the sine of k is positive? Why the sine of 100 is positive? Is there any reason? Are you with me? Why the sine of 100? Remember, k could be 100. And when I say 100, I mean 100 radian. Why the sine of 100 radian is positive? There is no reason with that. Why the sine of 200 is positive? The sine go up, down, up, down, up, down, up, down, up, down. Okay, so this is definitely the sine of k, cosine of k are definitely not positive. Okay, very good. Now, how I'm going to study the conversion of this series. Since it's not positive, integral test I cannot apply, limit comparison falls apart, and ratio test. That's the only thing I can use. Now, if you guys try the ratio test, it will get us nowhere. Okay, so the way I'm going to do that is I'm going to look at the series in absolute value. I'm going to ask myself, if I can prove it with absolute value convergent, it will converge. The benefit of the absolute value that now I have series with positive terms and I can use every test I want. So now let us see. Let me look at sine k over k squared. How can I prove that those are positive now? I am safe. Now, how can I prove that this one converges? Any idea now? So the reason I took positive now, so I can use all the tests I have. How can I show that this one converges? Anybody has any idea?
Could we use limit comparison test?
With what?
One over k squared.
Then you deal with the limit. I will try, but let me tell you what the problem is with the limit comparison. I'll tell you what the problem is because it's not really, you're not off, but let us say I do it with 1 over k squared. All right, and then I have to take the limit. So I take the limit. So I have to show you y over 1 over k squared. Okay, now if I do the algebra, I will get sine k over k squared times k squared over 1, which is the limit of absolute value of sine k. Now, what's the limit of that? All of you, I want you to think a little bit. What happened to the sine k when k go to infinity? Does the limit, what's the limit?
Does it not exist?
Exactly, do not exist. Absolutely correct. Why do not exist? Because the same reason, the sign keep bouncing up and down between -1 and 1, -1 and 1, -1 and 1, never get close to anything. I mean, that's the sign. We're not getting close to anywhere, therefore the limit does not exist. So limit comparison is a good idea, but it's not going to work with us. All right. I would like to suggest another test.
So then could we do the divergence test?
The divergence test. What does the divergence test tell me? So I will follow all of you and I will say what you, so the divergence test tells me that I have to take the limit as k goes to infinity of sine k over k squared. Okay? The question, what happened to this limit when k goes to infinity?
Goes to 0.
Goes to 0, correct, why?
Just because it would end up being a very small number over infinity. So
Exactly. So let me repeat what your classmate is saying. When k is large, what can we say about the sign of k?
it's going to be really small.
It's not small actually, but it's going to be less than 1.
Okay, yeah.
It's less than 1. It's crucial. It's not small. It could be 1. So what's happening here? The sign of k is less than 1. 1 over k squared. So when k goes to infinity, when k becomes very large, this one will go to 0. It means the sine k over k will be close to 0.
Can we use the alternating series test?
No. Why? I like everything you're saying, but I have to show you why I would say no.
Or is it because it's not decreasing?
Yeah, no, because I'm taking series with positive term now when I took the absolute value. Even without absolute value, it's not alternating. Because why sine of 1, to be alternating, I need positive, negative, positive, negative. But now if I write the term sine 1 over 1, sine 2 over 2, sine 3 over 3, why is sine 2 positive, sine 3 negative? There is no reason. Actually, it's not correct. So it's not alternating. Okay. Very good. Anybody?
So why does the graph, if sine's never going to be negative, why does the graph?
It will be negative.
When will it be?
It can be negative. But it doesn't mean sine 1 is positive and sine 2 is negative.
Okay, so it's not like a back and forth thing. It's kind of
No,
like
not for sine 1, sine 2, sine 3.
okay.
Remember, now here should be like, this is a 2 pi. This is 4 pi. That's all we know. So sine 1, it should be somewhere in here. 1 is pi is 3.4, right? So, I mean, we're not going to do that, but sine 1 should be probably somewhere here. Sine 2 is going to be here. So sine 1 and sine 2 are actually positive. Sine 3 is going to be positive. Sine 4 is going to be negative. So there is no alternating at all. You understand what I'm saying?
Okay, yeah, I understand now.
Yeah, so sine 1 is positive, sine 2 is positive, sine 3 is positive, sine 4 is negative.
Okay, yeah, I
Sine
see that.
5, I don't know. I think sine 5 is going to be negative. Sine 6 is going to be negative. And then I think sine 7 will be positive. So there is no pattern involved. It's not positive, negative, positive, negative. So again, I scratched. All right. Who would like to pitch in? So you guys are doing fine. You're trying all the tests. I'm trying to convince you they are not working.
Can we do the comparison test?
Here you are, comparison. Whenever there is sine, cosine, the test I told you, it's hard to use, you use it. That's the comparison test. And why the comparison test is the test to go. The sine k, the only thing I can control it with by saying it's less than 1 over k squared. Okay, that is, I can't compare it with anything. I cannot do nothing with it. The sign is problematic, but I have something very strong about it. I know it's less than 1. So the comparison test in this scenario kind of imposes itself. So it tells me that now sigma, the larger series converge. It means the smaller one converge. It will converge. So now the series. Sigma sine k over k is absolutely convergent because it converges in absolute value. Hence, it's convergent. Even without absolute value, it converges. End of the problem. Okay, so that's how we can use. So let me take you back because we.
I have a question.
Yes. Please go ahead.
Why do we know that? How do we know that sine k over k squared is absolutely convergent?
Because when I took it in absolute value, watch carefully how I did the argument. It's less than 1 over k squared. Am I correct here?
Yes.
Now, this series converge.
Yes.
Because a p series, p equal to 2.
And p is greater than 1.
Yeah, less than 1, bigger than 1. It means the smaller series will have to converge. Because if we add those terms, we don't blow up. Adding smaller terms, we're not going to blow up either. It means that this series is absolutely convergent because that's the definition of absolute convergence. Means in absolute value, it converges. Since it's a conversion absolute value, this theorem tells me, remove them, it will converge as well. End of the problem. So this theorem, absolute convergence, is used sometimes when we have complicated series that the terms are not positive, the terms are not negative. I actually don't know what to do with them. The ratio test falls apart. Then I take them absolute value, say, okay, the conversion absolute value, remove it, they will converge as well. And then, so these are the tests that we've seen so far. And then we studied the notion of conditional conversion that you have to review for tomorrow. They are those series that they converge by themselves, but when you plot the absolute value, they diverge. And the typical example, so the conditional convergent. This is not a test, it's just a definition that you should know. It means that if you take this series converge, but in absolute value, it diverges. Okay, who can give me quickly a quick example of that? Who can think of an example? What's the easiest example you can give me?
-1 to the k multiplied by 1 over k.
Exactly. This is a typical example. This is will converge by the alternating series test. When I plug in the absolute value, it will become 1 over k. It will diverge by a p series. So that's the summary of basically everything that all the tests that we've seen in this section. Now I'm going to give you a bunch of series and I'm going to ask you, not hard, which test do you think is the test that you should try? So that will be basically my question. So the question is, identify a convergence test. So we're not going to do the work, but we have to identify, based on what I told you, identify a convergence test. Of course, for some series, there is more than one test that will do, absolutely. But this is just an idea, a guideline. So I will start, I will give you a bunch of them, and I want you to tell me. K squared over 4k squared plus 3k. So usually you look like we did with integral. You look at and when we're integrating, you look at the function. Now here you look at the terms and you start, asking, what shall I do? Okay. All right, the first one. What do you think you will do? Quickly, so I can do at least 3 or 4 to elaborate every idea.
Divergence test.
Divergence test. That's very good. K squared over 4k squared. You should just look at it. I want you to be able to look at that. This one goes to 1/4 as k goes to infinity, non-zero, diverges. All right, so we're just looking at it, and this k squared over 4k squared, we should by now realize that this is really a problem. It means we are eventually adding 1/4 to 1/4 to 1/4 to 1/4. That's really the picture in your mind. Okay, this one, AK.
Hey, what do we do? What do we use for the first one?
Divergence test. For the first one.
All right.
Okay, now the second one.
Limit comparison test.
Limit comparison test. Absolutely. Because the term of the series involve only powers of k, constant power of k. They involve k squared. They involve k4. So they only involve constant power of k, definitely the limit comparison test. Forget about comparison. I don't even want to know. Limit comparison is the way to go. And what I should, so the reason I'm using limit comparison, it only involves constant power of k. Now, if you do the ratio in those scenarios, you will get the 1. If you ever try it by yourself, you will get an honest to goodness 1. That's where the 1 comes in the ratio test. Now let us see a little bit what shall I compare it with. And I will do it fast. The numerator is going to act like the square root of k squared. The denominator will act like 3k4. That's how we're going to pick my bk. All right, so it means it's going to be k over 3k to the power 3. I will not do the whole picture, but I'll just remind you. That will be my bk. All right, so limit comparison test, and I have to compare it with 1 over 3 squared. All right, another example.
Is it 1 over 3 cubed?
No, it's k over, oh, sorry, you're right, thanks. So 1 over 3k cubed. Thank you very much. And that will be my bk. 1 minute, sorry, guys. No, this is not for. Yeah, I'm sorry, guys. My son has to go to the doctor, and I have to get the paperwork for him. Yeah, this is the one. Sorry about that. All right. So another example. Sigma k 2 to the k over 3 to the k. Which series shall we do? Quickly. Peter, take mask with you. Give him mask, Roger. All right, quickly, which test? Ratio. This is Scream's ratio test. Whenever a series, the minute you see a series in general, where you have exponential terms, 2 to the k, 3 to the k, 4 to the k, ratio test is the way to go. Now, suppose I give you the following, sigma k 2 to the k over 2k factorial. Which test?
Ratio.
That's ratio. Those tests scream ratio test. All right. One more example. Suppose I give you the following. -1 to the k over k plus 1 to the power 4. Which test?
Alternating series.
Alternating series test. That's not hard because you have -1 to the k divided by k plus 1 to the power 4. This is obviously alternating. No question asked. It's not like the sign k, which we have no idea what's happening. Absolutely alternating. Both condition of the alternating series test will be satisfied. That's an alternating series test. All right, the last one I had on my list, and I will finalize, is the following.
Comparison test.
Comparison test, absolutely. Whenever we have the sign k, we go after the comparison test. And what shall I compare it? First, they are positive. Am I right? Yes or no? Is this a series with positive term? Because that's the only place I can use the comparison test. Are those positive? Yes or no?
Yes, because if the sign is negative, when you add 1, they'll still be positive.
Right. This the smallest value the sign k can take is -1. So when you're adding 1, so that's the sign between hover between -1 and 1. So when you add 1, it's going to go up here. So it's always going to be positive. Okay. Now, what shall I compare it with, though? Comparison has to be solid comparison. We have no choice.
Be 2 maybe over.
Very good.
Okay.
It's 2. Not maybe, absolutely correct. Why are you correct? 2, because the sign of k is always less than 1, regardless what k is. Regardless what k is, the sign is always less than 1. Okay. When I'm going to add 1 to it, it's going to be always less than 2. Okay, and now we're done. The largest converge. It means the smallest will have to converge. So whenever we have sign, I'm really limited in my, I use the comparison because there is nothing that will control the sign but the comparison test. All right, so of course that's it for today. Tomorrow we're going to start chapter 11, which is the idea of approximating functions by polynomial. So the idea of approximating any functions you have, we're going back to function, any function, no matter how complicated it is, the idea is to start approximating it by polynomial. And why we studied series is actually will be clarified in the next section. All right. So the class is dismissed. Anybody has any question, as usual, can remain.